Good day to each and everyone. We are here once again for another interesting discussion in science. In our previous discussion, we talked about the different image formations in spherical mirrors. This time, in this video, we will be talking about another way of describing the images that are formed in spherical mirrors through mirror equations and magnification equation. So, just sit back, relax, and enjoy this moment of science with Mr. Rabino. In our previous discussion, we talked about the different image formations in spherical mirrors. In this video, we are going to tackle another way to describe images formed by spherical mirrors through quantitative analysis. In this analysis, we are going to use the mirror equation as well as the magnification equation. So without further ado, let us now start our discussion for this video. Mirror equation and magnification equation are two of the equations that we can use to quantitatively describe the images that are formed in spherical mirrors. So let's describe further what are these equations. A mirror equation is a quantitative description of an image formed in a spherical mirror. And in equations, it is stated as 1 over d sub o plus 1 over d sub I is equal to 1 over f. Now, let us further describe these variables. D sub o is the distance of the object from the mirror. D sub I is the distance of the image from the mirror. And f is our focal length of the mirror. So this equation, in a first glance, it looks so complex, but in fact, it's quite simple. It tells us that the image characteristics of a convex or a concave mirror are actually dependent on the object's distance from the mirror as well as the focal length of the mirror. So, in order to complete our description of the image formed by spherical mirrors, we also have another equation that we can use that we call as the magnification equation. Now, in a magnification equation, or M, magnification simply means the ratio between the size of the image and the size of the object. Or, in other terms, it could also be the ratio between the distance of the image from the mirror as well as the distance of the object from the mirror. Okay? Now, magnification just simply tells us how big or how small an image gets when an object is placed in front of a concave or a convex mirror. So, in equations, we can describe this magnification as follows. M is equal to h sub I over h sub o. It is also equivalent to negative d sub I over d sub o. Now, to describe these variables, M here stands for magnification. Take note that the magnification has no unit, okay, because it is a ratio. H sub I is the height of the image. H sub o is the height of the object. D sub I is the distance of the image from the mirror, while D sub o is the distance of the object from the mirror. Now, in order for us to summarize our descriptions of the image formed by spherical mirrors through this analysis, we need different sign conventions to remember. Okay? So what are these sign conventions? Let's show that one right now. F is positive, or the focal length is positive for a concave mirror, while F is negative for convex mirrors. Now, D sub O is always taken as a positive integer or value. Okay? Now, D sub I is positive if an image that is formed is real, inverted, and in front of the mirror. And how about if Di is negative? If Di is negative, the image is virtual, and at the same time, it's upright, and it's behind the mirror. Now, if M is a positive number, that is an upright image. Okay? And if m is a negative number, that means it is an inverted image, or the image has a different orientation than that of the object. So, these are the sign conventions that you need to take note when we are going to solve and compute for variables using mirror equation and magnification equations. So, in order for us to practice solving problems involving mirror equation and magnification equation, of course, let us immerse ourselves to some sample exercises. Okay? So let us show right now some sample problems here on the screen. Number 1. An object is located 45 centimeters in front of a concave mirror whose focal length is 15 centimeters. Where is the image formed and what are the characteristics of the image? Let's pause, think, and analyze. Okay, now to solve this, let's just switch my screen to our solution board. Okay, let's switch that right now. Okay, there, I've written the problem in this application. Now, it says here that where is the image formed and what are the characteristics of the image. So first, in every problem, for you to be guided, always write what is asked in the problem. So what is asked in the problem here is our d sub I, or where is the image located. So that's why we denote that as d sub I. That is unknown, so that's why we put that a question mark there. And of course, let's always write the given variables that are present already in the problem. So it says in the problem that an object is located 45 centimeters. So that is why our d sub O here is 45 centimeters. And it says also that the focal length of this mirror is 15 centimeters. So F here is 15 centimeters. Now, since this is a concave mirror, we are going to use a positive sign for this value because a concave mirror always has a positive focal length. Okay? So, what are we going to do right now? Now, let's solve for the equation. And since these variables di, do, and f are found in the mirror equation, we are going to use the mirror equation for this example. So let's write the solution right now. Let's write the whole equation, which is 1 over f is equal to 1 over do, oops, please don't fail my hand, plus 1 over di. Alright, wow, I've written it. Congratulations. Okay, so let's solve. Substitute now the given variables. So our f here is 1 over, let's substitute that, 15 centimeters. Oops, forgive my handwriting, which is equal to 1 over do. Our do here is 45 centimeters. Plus 1 over, and since our di is unknown, we just write it as it is. So let's leave it 1 over di. Now, to solve and isolate the unknown variable here, we will transfer 1 over 45 centimeters on the left side of the equation so that 1 over di in this case, I will color that it will be isolated. Okay? So let's just move down. And to isolate that, we need to transfer this 1 over 45 centimeters to the other side of the equation. And always remember that if a certain integer, a number, is transferred to another side of the equation, its sign also changes. So what happens is, first, let's write down first 1 over 15 centimeters. Now, since in this side of the equation, it was still positive, since it will be transferred right now to another side of the equation, it will be a negative integer, or number rather. So it will be minus 1 over 45 centimeters. Okay? Which is equal to 1 over di. Now that di is isolated, we need to perform an operation between 1 over 15 cm and 1 over 45 centimeters. And since both of them are dissimilar fractions, we need to find a common denominator for the two denominators of these fractions. So, what way can we do that? We are going to look for the LCD of the denominators 15 and 45. So, what is the LCD of 15 and 45? Well, you're right. The LCD is 45 centimeters. Sorry, let's rewrite that. 45 centimeters. Okay? Why 45? Because 45 can be divided by 15 and of course can be divided by itself. Okay? So let's proceed. How are we going to do this? First, divide this LCD to one of the denominators and then multiply it to its numerator. Okay, so let's do that. 45 divided by 15, that's 3, right? Times 1, because that's its numerator, so it is still 3. Okay? So 45 divided by 45 is 1, right? Times 1 is 1. And don't forget to copy the operation from the top, okay? And this will be equal to 1 over di. Okay, we're almost done. Let's just transfer this on the other side, okay? So that we can continue. Next thing is, do this operation. 3 minus 1, that is equal to 2. And then copy the denominator over 45 cm, which is equal to 1 over di. Alright. Okay. Now, since we want to obtain the value for di, we need to somewhat do some, mathematical technique in order for us to be able to get the value for di. Because we are not yet done here. Okay? We need this somewhat to be in our numerator instead of being at the denominator. Okay? So to do that, we need to what? We need to use what you call as cross multiplication. There are other ways that you can do to extract di, but I like cross multiplication because it's much simpler to perform. It's a direct way. So we just cross multiply the numerator of one fraction to the denominator of the other side of the equation. So to do that, let's try it. 2 times di will be, of course, 2 di. Right? It is equal to 1 times 45 cm. Of course, that is 45 cm. Now that we have obtained this result, it's time for us to extract di. And to do that, we need to divide the whole equations by 2 over 2 so that we can cancel this 2 here, and what remains is our di. Okay, you see that? That's the purpose of that one. So we have here di is equal to 45 centimeters divided by 2. So our di here will be roughly equivalent to 22.5 centimeters. Okay, now let's box that one because this is now our final answer. Di now, or the distance of the image from the mirror, is 22.5 centimeters. Okay, now we are not yet done actually here because the question is also asking us what are the characteristics of the image. Now, how do we characterize an image just based from the value of its di? To do that, let's get back once again to our sign convention. Okay, let's get back from that sign convention right now. So the sign convention would somewhat show us that if di is a positive, it's real, inverted, and in front of the mirror. But if di is negative, it is virtual, upright, and behind the mirror. So let's use that sign conventions as our reference. So let's get back to our equation board. Since the value of our di here is a positive number, that means that our image is real, inverted, and it is in front of the mirror. So for you not to be confused about that, let's go back again to the sign convention. There. See that? So let's get back again to our equation board. So 22.5 centimeters. So let's write that one, the characteristics here, as, since if it is positive, it should be real, it should be inverted, and it should be in front of the mirror. There. Okay. And that completes our image description in this problem. See? It only seems to be complicated, but in fact, if we are going to already perform the solution, it's actually relatively not so complicated one. Okay? So, I guess we are done with sample problem number 1. So, do you want more other problems? Would you like to solve another equation for this? So, if that's so, then let's show another problem for you to work on. Okay, so let's show problem number 2. A trophy is 30 centimeters in front of a concave mirror whose focal length is 15 cm. Where is the image formed and what are the characteristics of the image? Pause, read again, and think. Okay, so let's solve this problem. To do that, let me switch to my solution board. Okay, so our solution board is still showing our first problem. So let me switch to the second problem. It's here. All right. So, of course, as always, write what is asked in the problem. What is asked here? So, what is asked is, where is the image formed? So, that means that DI is still being unknown here. Okay? DI is still unknown. Now, how about some of the given variables already in the problem? Let's look at the problem. The trophy is 30 centimeters in front of a concave mirror. So, this will serve as our distance of the object. Okay? That is 30 centimeters. Okay? Let's complete that. 30 centimeters. Okay? Okay? And whose focal length is 15 cm. So, our 15 cm is this one. Okay? 15 cm. I think we did not miss any more given problems or given variables. Now, F here is still positive because it is a concave mirror. Okay? Since it's a concave, so we are going to use a positive focal length. Now, of course, we need to use the mirror equation in this case. Now, that is 1 over F is equal to 1 over DO again plus 1 over DI. Oh, I'm getting used to writing with these things. Okay, so let's check. 1 over and substitute over 15 cm. Okay, let's substitute all those values right now. It's equal to 1 over DO, that's 30 cm. Oh, plus, okay, DI is still unknown. Okay, and of course, as what we did a while ago, we need to transfer this to the other side of the equation so that we can isolate our 1 over DI. So, let's do that. 1 over 15 cm minus, take note, it was a positive number here, but when you transfer it, it becomes a negative. So, minus 1 over 30 cm, which is equal to 1 over DI. Okay? And the same as always, we need to find the least common denominator since we cannot operate with a dissimilar fractions. Okay? So to operate the two equation, we need to find the LCD. So what is the LCD of the denominators 15 and 30? Yes, you're right. That is 30 cm. So why 30? Because 30 can be divided by 15 and 30 can be divided by 30. So let's continue. 30 divided by 15, that is 2, times 1, which is the numerator, it is still equal to 2. Okay? Copy the operation, the minus sign. 30 divided by 30 is equal to 1. Times 1 is of course 1. So that is 1 over di. Okay? So let's transfer again on that other side. Okay. 2 minus 1 is of course 1, right? So 1 over 30 cm, which is equal to 1 over di. Right? So all we need to do again is to cross multiply. Okay? 1 times di is equal to di. Write the equation sign. 30 centimeters times 1 is of course 30 centimeters. And since di, we cannot do anymore because that is do anything anymore because that is already the answer. So our di here is 30 centimeters. Okay? So di is 30 centimeters. So how are we going to check once again if what are the characteristics of this image? So again, we need to use our sign convention. So let's check again our sign convention. If di is positive, that is a real, inverted, and the image is in front of the mirror. And if di is negative, that is a virtual image, upright, and behind the mirror. And since our di here is a positive integer or number, or as a positive magnitude of value, that means that our image characteristic here is real, inverted, and in front of the mirror. And that completes our solution for this problem. Okay? Now, sir, I haven't seen that the magnification equation is applied here. Okay, that's a good question. Now, if this question will ask you how big is the image, then that's the time that you are going to use a magnification equation. So how are you going to use that one here? So for example, let's add another problem in this case. So let's say I'm going to ask how big is the image? Okay? How big is the image right now? So in order for us to calculate that one, we need the magnification equation. So since we are looking for how big the image gets, so let's use the magnification equation. So let's recall that, let's write this as letter B. Sorry. Let's just use a line here, separate that. Okay. Let's look at the magnification equation. M is equal to HI over HO, right? Or we could use this negative DI over DO, right? Now, if you're going to look at the problem, there is no HI and there is no HO given in this problem. So technically, we cannot use this equation here. So that is already out of the question, okay? We cannot use that one. We do not use this, okay? So that means that we can use this equation instead to get the magnification or how big the image is from the mirror. Now, to do that, let's look at where is DI and where is our DO. Okay? So, let's check. M is equal to, what is our DI once again? Based from our calculation, DI is 30. Take note that there is a negative sign already there from the equation, so we just need to copy that one. Negative, then open parenthesis. Our DI is 30 centimeters. Okay? Now, divided by what is our DO? our DO is still 30 centimeters. Oops. So of course, if we divide that, we cancel this unit, and 30 divided by 30, that means that our M is equal to 1. And that is already our final answer. Oops, take note. Don't forget, there was a negative sign here. So our answer is negative 1. Okay? So M is negative 1. So what does negative 1 mean there? So for you to understand the values of magnification, here are the following notes that you can use. Okay? Let's refer to this notes class. Look at this. If M is equal to 1, take note of that. I'm sorry. If M is equal to positive or negative 1, that means that the image is equal or the same as the size of the object. Okay? M is equal. Okay? Now, how about if M is greater than 1? Okay? If M is greater than 1, that means that the image is bigger. Okay? Bigger than positive, negative 1, that is bigger. Now, if M is less than the positive and negative value of 1, that is, the image is smaller. Okay? Remember all these things. Okay? Smaller. So M here is a negative 1. So M is equal to negative 1. So that means that it has the same size as that of the object. But why is it negative, sir? What does the negative sign there mean? So if we look at again our sign convention, okay, look at again our sign convention. If M is negative, that means that our image is inverted. Okay? Okay? So that only signifies that our image is inverted because of the M is negative. Okay? And that actually ends our sample problem number 2. Okay? So I hope that all these steps are so clear to you as of this moment right now. So there. Let's look at that. Look for our image there, and of course this is now our answers. Okay, now let's move on to another example problem for us to really instill this in our minds. Look at another sample problem. Okay, and this time I want you to do this on your own. Okay, I'll give you some time. You can pause the video for you to think and to solve this problem that I'm going to post on my screen right now. Okay, so let's begin. A 4.0 centimeters light bulb is placed at a distance of 45.7 cm from a concave mirror. Okay, let's make this interesting. Okay, let's make this interesting. I'm going to change this mirror into a convex instead. Convex mirror having a focal length of 15. Determine the image distance and the image size. Okay, let's make that as a convex right now. Okay, so pause, think, and then you can start solving on your own. You can pause this video and solve this problem on your own. And if not, in a few seconds, I'm going to perform the solution for this problem. Okay, so let us now solve for this problem. Let me switch again to my solution board. Okay. Now for our solution board, where's my problem? Here. Okay, let's change that one. That is not a concave anymore. Let's erase this one. Oops, sorry. And then let's change that one to convex. Okay. From a convex mirror. Okay. From a convex mirror having a focal length of 15.2 centimeters. Determine the image distance and the image size. Okay, let's start. Of course, always start what is asked in the problem. Okay, what is asked in the problem is the image distance still, di. That is a known. Okay, what are the given variables in the equation or in the problem rather? We have a 4.0 centimeter light bulb, meaning to say that's our height of the object. Okay, because it says here 0.0 centimeter tall, so that should be the height or the size of this light bulb. So HO here is 4.0 centimeters. Okay, now it says here also that the distance is 45.7 centimeter from a convex mirror. So DO here is 45.7 centimeters. Okay, and who having a focal length of 15.2 centimeters. Now 15.2 centimeters. Now this time it would be a little different because our focal length will now have a different sign. Okay, because if we look back once again to our sign conventions, okay, let me go back to our sign convention. Let's check that once again. Okay, F is negative for a convex mirror. Okay, so in this case we need to use a negative sign for our focal length because it is now a convex mirror. So we are now going to use a negative sign in this case. Okay, so remember that negative sign over there. Determine the image distance and the image size. Okay, to do this, first we need to have our mirror equation. Always start with the mirror equation. Okay, so solution is start with the mirror equation. 1 over F is equal to 1 over DO plus 1 over D sub I. Okay? Oops, commercial break. Okay, so there was just a car passing by right now, so let's just don't mind that. Okay, now our focal length here is 1 over negative 15 centimeters. Okay, don't forget the negative sign because that's important. Is equal to 1 over DO. Our DO here is 45.7 centimeters. Okay, 45.7. Sorry, let me just write this in a clean way. 45.7 centimeters plus 1 over D sub I. Okay, now what's next? Again, transfer or transpose one of the variables in the other side of the equation. So in this case, so that we can isolate 1 over di on this side, we need to transfer 1 over 45.7 centimeters. Okay, so what happens will become like this. Okay, follow 1 over 15 centimeters. Let me just transfer the negative sign here so that everything will be proper. So sir, why did you transfer it, sir? Because 1 over negative 15 is just equivalent to negative 1 over 15. It's just the same. Okay, so we can just put it there to make things easier later. Okay, minus 1 over 45.7 cm is equal to 1 over di. Okay, what's next? We need to find the LCD. But how are we going to find an LCD, sir? That the other one is a the other denominator is 15 cm, and the other one is a decimal. You don't have to worry about that, right? All you need to do is that in case that the LCD is too difficult for you to find, you can always how do you call this? You can always resort to this. How do I call this? Maybe this is just a practical way, of looking for an LCD. What I usually do here, class, is that I will just multiply the two denominators. Okay, I will just multiply that one, and then I'll be able to get my LCD. So let's try that one. Okay, so 15 times 45.7. What is that? Let's calculate that right one. That one right now. So that would be 45.7 times 15. So you will get a result which is equivalent to 685.5 and right centimeters there. Okay, so we can now already start calculating. Now what's good about this one is because if you are going to multiply this to, what happens is that when you divide this to the denominator, what happens is that when you divide these denominators to its when you divide this LCD rather to these denominators, what happens is that it becomes like this. This one will go here. Sorry. Control Z muna. Okay. This value or this number here will be here. This one will be here. Or maybe we can use other colors so that you will not be confused. So this value here, this denominator will be here, and this value here will be here. For you to double check that one, it's like this. Because 685.5 divided by 15 is equal to 45.7. So that's what I'm trying to say. 45.7. Take note, there's a negative sign here, so don't forget that. Negative. Minus 685.5 divided by 45.7 is equal to 15. That's what I was trying to tell you a while ago. Okay? 15 is equal to 1 over di right now. Okay? Now all you need to do is once again just operate what is happening here on the numerator. Negative 45.7 minus 15 is just the same as adding 45.7 plus 15. Okay? So negative 45.7 minus 15 is equal to around what? Negative 60.7. Right? So that's negative 60.7 over 685.5 cm. Okay? Which is equal to 1 over di. Okay? Now, what are you going to do this time? So, always remember, once you reach this point, it's now time for you to cross multiply. Okay? So, what happens is that you cross multiply 60.7 times di, that will become negative 60.7 di. Okay? Which is equal to 685.5 cm. Okay? Now, in order for you to isolate di, you need to divide the whole equation by negative 60.7. Divide the whole equation by negative 60.7 cm. Okay. Sorry. Negative 60.7 only. No unit. Okay. Sorry for my handwriting. Negative 60.7. Okay. So that we can cancel this, and di remains. Okay? Now, if you divide 685.5, okay, divided by 60.7, Okay, what's the result? Wait for a while, let me calculate that one. 685.5 divided by 60.7. That should, sorry. Is that correct? 685.5 divided by 60.7. Okay, so you will get a result of around di, which is equivalent to negative 11.29. So if you calculate this, you will get a lot of decimal points, but let's just stop at the second decimal place. Okay, so our di here is negative 11.29 centimeters. Okay, so how many of you got the correct answer? So if you got negative 11.29 centimeters, then congratulations, that is a correct answer. Okay, if not, please review and just rewind this video for you to follow through the process. Okay, now how do we describe this image here? Okay, the image here is a negative di. So if we are going to get back to our sign convention once again, di is negative. That means it's a virtual image, upright, and is always behind the mirror. So our di is a negative one. So we are going to describe our di as something like this. So let's write our description. Since it's a negative, so this is virtual, this is upright, and on the other, or behind the mirror, or on the opposite side of the mirror. That's how we are going to describe this image right now. Now, the question also is asking us, determine the image distance and as well as the image size. No? Let's not forget about this. No? Nag-a-ask din, what is the image size? Okay? So how are we going to get that one, or to calculate that? So to get the image size, all you need to do is just use the magnification equation. Okay? Now for the magnification equation, it is m is equal to, let's just use the other one a while ago, negative di over do. Okay? So m is equal to negative, there is a negative sign already, negative, our di a while ago is 11.29 centimeters. Okay, let's use that one, negative 11.29 cm. Okay, so there's a double negative there, divided by, where's our do? Our do here is 45.7. Okay, that is 45.7 cm. Okay, now to do that, take note, there's a double negative here. A negative times a negative is always a positive, so it will become 11.29 cm divided by 45.7 cm. Okay, now of course cancel these units because they are both in the numerator and denominator. So when you divide that one, you will get a result of how much? Okay, how much is the result for that one? So let's calculate that in my calculator for a while. 11.29 divided by 45.7. That's 0.25. Around 0.25. Okay, so 0.25. Let's box that one, so don't forget that that is our final answer. 0.25. Now that is our magnification. Okay, now since it's a magnification, what does m 0.25 mean? If we go back here, take note, if we go back here, if m is less than the positive and negative value of 1, that means that the image is smaller. So if we are going to look at here, our m here is less than 1. So that means that our image is smaller. But how small is the image? Okay? Now to get the image height, no? Just to get the image height, all you need to do is just multiply this magnification times the height of the object. Okay? So to do that, when we calculate the image height, all we need to do is that hi is equal to magnification times the height of the object. Okay? So hi here is magnification, which is of course 0.25 times what was the height of our object? You're going to check. That is 4.0 centimeters. So that is 4.0 cm. So hi rather 0.25 times 4.0 centimeters. How much is that? Okay, 4 times 0.25. That is 1 centimeter. Okay, so this is now our image height. So if you will be asked how much is the height of the image, all you need to do is just do these steps right now. So from the start, we started with the mirror equation to get our distance of the image. And from that, since we got our di, we solve for the magnification equation to get the magnification number, or how bigger or how smaller is the image from the object. From that, we can actually calculate the actual size of the image. Okay, so that is how we are going to calculate step by step and use the mirror equations and magnification equations in our solutions. Okay, and that ends our discussion about the quantitative analysis in the image formations in spherical mirrors through mirror equation and magnification equation. So I hope that you have learned something out from our discussion for this video. So my tip for you to master solving mirror equations and magnification equations is to constantly practice, and of course, to always consult your teacher whenever you have problems regarding solving these equations and problems. So, once again, thank you so much for staying tuned with me, and I hope that I have brought something meaningful throughout this discussion. This is Sir Rabino once again, saying goodbye, and thank you so much for your participation. See you next time, my dear students.